Hello gents, now we're going to try and solve some calorimetry problems where two substances are exchanging heat energy. One is losing, one is gaining. Our first example says that 240 grams of water, initially at a temperature of 20 degrees Celsius, are mixed with an unknown mass of iron, which is initially at 500 degrees Celsius. When thermal equilibrium is reached, meaning the temperatures of both substances reach one common temperature, the system has a temperature of 42 degrees Celsius. Find the mass of the iron that was put into the water. Iron has a specific heat capacity of 0.450 joules per gram degree Celsius. Now to set this up, we know my relationship is Q of one thing is equal to Q of the other. Now, first thing we have to do is figure out which one loses heat, which one is gaining heat. Initial temperature of my water is 20 degrees Celsius. Initial temperature of my iron is 500 degrees Celsius. Iron's hotter. Iron will be losing heat to the water. So we can make iron here Q of iron. It's losing heat. What's gaining heat is the water. Okay, now what does Q mean? Q is equal to MC delta T. So this will be negative MC delta T. And we're talking about iron here will be equal to positive MC delta T. We can leave out the positive sign because it's understood here. Now we fill in our values. We want to know what the mass of the iron was. But let's fill in everything else before we do that. So we have negative, the mass of iron is unknown. Specific heat of iron is 0.450. The change in temperature. Well, the iron started at 500 degrees Celsius, and the entire system at the end reached a temperature of 42 degrees Celsius. So that's both final temperature for the iron and the water. That's why they're in thermal equilibrium, because they both reach the same final temperature. So final temperature is 42 degrees Celsius for the iron, and it started at initial temperature of 500 degrees Celsius, T final minus T initial. This is equal to the heat of water, the heat gained by the water. To be more specific, the mass of my water is 240 grams. That's the M. Times the specific heat of water, which we know is 4.184 joules per gram degree Celsius. Multiply times the change in temperature of my water, delta T. It started at a temperature of 20 degrees Celsius and ended at 42 degrees Celsius. So final is 42 degrees Celsius, just like my iron, minus initial, which is 20 degrees Celsius. And there you go. That's my setup. Now I simply solve for my unknown, which is mass, which is what I'm being asked to solve for. Find the mass. So 0.45 times 42 minus 500 will give you a value. But let's isolate M first. So divide both sides by 0.450 joules per gram degree Celsius. That would cancel out this, and divide that by this side. When I do that, I'll get approximately, and I'll write this up here, I'm running out of room, that negative M equals 22,901.52 divided by 206.1. Now that would be what this stuff is. Now let's see if everything, all my units and stuff are correct. So grams cancels with grams. Degrees Celsius will cancel with degrees Celsius. Grams still here. Degrees Celsius will cancel with degrees Celsius. Joules on top cancels with joules. I'm simply left with units of grams. So this will be grams down here, just 0.4450 times 42 minus 500, excuse me. But this is going to give me a negative number, which makes this negative. So 22,091.52 unitless up here divided by 206.1 grams. Negative is going to cancel with that negative. Mass is going to be equal to 107.2 grams. So the mass of iron that you put into that water was 107.2 grams, and that caused a temperature change from 500 to 42 degrees Celsius. That's one problem. A different spin that could be put on this is solving for a different variable. Rewind that if you have questions. Go through the mathematics yourself. Please do not take my word for any of that. Do it yourself. Different problem. If 24 grams of sodium chloride with a specific heat of 0.864 joules per gram degree Celsius, that's the symbol for a specific heat, C sub P. We've been calling it just C, but sub P can be put in. This sodium chloride is at 25 degrees Celsius, and it's mixed with 272 grams of mercury at 50 degrees Celsius. If this is so, find the final temperature of the mixture. So you're finding TF. The specific heat capacity of mercury is 0.140 joules per gram degree Celsius. Now the same setup applies here. The Q lost is equal to the Q gained. First off, what's losing energy? Well, we see which one is at the higher temperature. Mercury is at a temperature of 50 degrees Celsius, whereas sodium chloride is at a temperature of 25 degrees Celsius. So our mercury is what is losing heat. So we can put that as mercury. I'll put merc. And what's gaining is our sodium chloride, NaCl. So as I go over here and I put this in MCAT form, we'll start to see this develop. This is of the mercury. So the heat of the mercury is equal to the heat gained by the sodium chloride, which is also governed by the same formula, but it's the heat gain. Now I'm going to fill in my values. And I'm going to fill in, as for delta T, I'm going to put TF minus T initial. So I have minus my mass of my mercury, which is 272 grams, times my specific heat of mercury, which is 0.140 joules per gram degree Celsius, times the delta T of my mercury. Will mercury finish or at TF? We don't know. We're asked to find the final temperature. That's subtracting the initial temperature of mercury, which is 50 degrees Celsius. And that's our MC delta T for mercury. This is equal to MC delta T of NaCl. The mass of NaCl is 24 grams. Times the specific heat, 0.864 joules per gram degree Celsius, times the change in temperature. Change in temperature is TF minus TI, which is 25 degrees Celsius. I wish I had written on a straight line because I need all this space. But we'll see. Now, I want to simplify as much as possible. So 272 times 0.140 will give me a negative 38.08 joules. My grams cancel here. Joules per degree Celsius. Multiply times TF minus 50 degrees Celsius. And I'm going to simplify on this side as well. 24 grams times 0.864 joules per gram degree Celsius. My grams cancel out. And I'm going to multiply those two together, and I will get 20.73 joules per degree Celsius times TF minus 25 degrees Celsius. Now here's where some algebra knowledge will come in handy. Here you're going to do the distributive property into this quantity here. So this is going to distribute into the TF and then distribute into the 50 degrees Celsius. Same here. I'm going to distribute 20.73 to the TF and to the 25 degrees Celsius. So when you do that, you get negative 38.08 joules per, these are units, whereas this is a variable. Know the difference. These are units, but this is a variable that you're solving for. Times T sub F. Minus, you have negative 38.08 times negative 50. So this is going to be a plus. And you will get 1904 joules. Why joules? Because joules per degree Celsius times degrees Celsius is going to cancel out your degrees Celsius. So you have this on that side of the equation. It's equal to distributive property into this here as well. 20.73 times TF is 20.73 TF. Minus positive number times a negative number is going to keep that number negative, so you keep that minus sign there. So 20.73 times 25 gives you 518.4 joules. Now if we look, we'll have like terms. Some like terms here are 20.73 TF, negative 38.08 TF times TF. Those are like terms, and these are like terms as well in units of joules, just like a standard algebra problem. I'm going to bring this up there in the simplified version. So what I'm going to do is isolate my variable. I want to isolate TF. First I have to combine them though. I want to keep it on the positive side, get these negatives out of here, so I'm going to add this negative to both sides. So plus 38.08 joules per degree Celsius, TF, which cancels it from this side, add it to this side, plus 38.08 joules per degree Celsius, TF. At the same time, actually, I'm not going to do that at the same time. I don't want to confuse anyone. From that, I'll get 20.73 plus 38.08 gives you, obviously, 58.81 joules per degree Celsius times TF. That's on this side. So I'm going to write that over here. And I still have a minus 518.4 joules over here. Now on this side, I only have the 1904 joules left. I still want to isolate this variable, so I'm going to add this to both sides. Cancels over there. Plus 518.4 joules. 1904 plus that, 518, give you approximately